A wide range of topics, including the basic and the advanced soil mechanics, and various case histories, including the basement excavations, tunnelings, power foundations, pipe jackings, and so on. Mostly involving three-dimensional modeling using the Midas GTS NX. That shows the software is well tested for industry use. Now, analysis in geotechnical is complex simply because we are dealing with three phases material, that is the solid, water, and air. Now, in rock mechanics, it's even harder because we are dealing with the structural joints. Human mind cannot handle interactions, problems in real life problems. It's too complex. So we need the tools to help us to do the jobs. And Midas GTS NX has been doing well on this. Okay, sorry. So today I'm going to show you 4 project applications using the software. There's one similarity among the 4 case study. That is the modeling structures in the clay or on the clay involve clays. So for every case study, there are comparisons between our modeling results and also the measurements that they will boost your confidence level in using the software. For case study number 1, I'll be talking about the consolidation settlement of an airport in Cambodia. The next one will be a failure of a jetty due to accumulations of silt on the slopes along the river. And number 3, I'm going to show you the floating pile design in soft clay, a case study also, our project. And number 4 is not in the in the advertisement. It is the negative skin friction in settling ground. I think it's very simple, but it's very interesting. So I have results, so I'm going to show you here. Now, as we all know that the soft clay exhibit the following characteristics. The clay is more compressible than the sand and is less permeable than the sand, and it has lower strength compared to the sand. And the shear strength is dependent on the stress path, whether it's going to the left, going to the right, dependent on the stress, on the loading. Its creep behavior is much more profound compared to the sand. And when you model your structures on soft clay, your software must be able to simulate the generations of excess water pressure due to loading or soil movement. Then your software must be able to simulate also dissipations of the excess water pressure. And because the clay are generally compressible and less permeable, therefore you expect larger deformation, and therefore more convergence problem you're going to face. And when you carry out analysis involving clays, it's going to be a time-dependent analysis, and the analysis is dependent, the result is dependent on where you apply your load. Okay, so for instance, you apply a load at day 1 compared to apply your load at day 10 is a completely different story. For soft clay, modified chem clay is doing very well. And for stiff clay, you may use a subsoil creep model or subsoil model because it can model better the softening behavior. And for stiff soil, hardening soil model is more than adequate. There are many similarities between the sand and the clay. They both have the memory on the stress state and they exhibit critical state model. And now we have North Sand model in Midas GTS NX. And when you combine these together, you will have the unified model in the market, CSM model. Now we go to the first case study. It's an airport runway. The objective of this exercise were to establish the input parameters in our numerical model, and then we use the input parameters to calculate the secondary consolidations of the runway. And we also, during the simulations, we also compare with the measurement, a lot of comparison between the measured and the model results, compare against settlement, deflections, pore pressure, and so on. So it is a very good case study, okay, to show that Midas GTS is really a powerful software. We then extend, after that we calculate the long-term settlement for the airport runway. That's what the client wants to know. Now this is the layout plan for the airport runway. It's not working. Okay. So there are 3 trial embankments in this runway. The test embankment number 1 is, we name it trial embankment, okay? And there are 2 other trial embankment in the airport runway. One is called, we call it transition zone, and the other one is called zone 4. There were 6 boreholes sunken into the site, sunken into the ground, borehole 1, 2, 3, 4, 5, and 6. And there were 10 CPT used sunken into the ground, CPT 1 until CPT 10. So this is the general layout of the problems. The undoing shear strength from the field wind shear test indicated that the clay has undoing shear strength of about 15 kPa over the top 12 meters. And the moisture content is around 35%. Liquid limit is around 40%, plastic limit is about 20%. The plasticity index is about 20%. And the liquidity index is about 0.8. The moisture content on all the boreholes are quite consistent, except for borehole 6, where you can see the larger value for every moisture content plot in the graph. If you put all the information into plasticity chart, then you can see that generally the soft clay can be categorized as a low plasticity clay, except for borehole 6 at the trial embankment area, which is a bit softer. The compression ratio is about 0.2. Okay, the recompression ratio is around 1/3 of the compression ratio, and the E0 is about 1.1, except for borehole 6. The permeability from the lab test, this is permeability from the lab test. Okay, plotted against applied pressure. If reduced with increasing applied pressure, the measured permeability is around 5 to the power minus 10 for the kV, and the CV is around 2 meters square per year, and C alpha, which is coefficient for secondary consolidations, is around 0.004. And we'll come back later, but I'll show you now is that the back calculated kV for our embankment for a best match is around 1.5 to the power minus 9, a bit higher, but not too high compared to the lab test result. But the C alpha value is a bit high. From the back calculations, it's 0.012. I'll come back to this later. Now, C alpha is a coefficient for you to calculate the creep. Can be obtained by extending the conventional one-dimensional consolidation test. It's simply extending the test by holding the sample for another 24 hours. And you can plot this type of graph, compressions versus the time, and then you can get the C alpha from the gradient of the curve. Now, C alpha is best correlated to CC value. We correlated the C alpha to CC value of 0.05 here, 0.025. That will give the C alpha of 0.012 and mu of 0.005. That give the best match of the back analysis. Now you can refer also to the Mesri and Feng's work. They have done a lot of works on this to calculate to correlate the C alpha to the CC value for different type of materials. Our experience is that it is more reliable to use the correlations to C alpha to CC compared to your lab test. Now this is the geometry of the tri-embankments. The embankment height is 4.1 meter, not very high. The soft clay is 10.5 meters. And the soft clay was divided into thinner sub-layers, 4 layers with slightly change of compressibility, follow the 1D consolidation results. And below the clay is residual soils, not very important. The water level is at the ground level. The PVD will install below the main embankment here. The spacing of the PVD was 1.2 by 1.2 triangle in pattern. And at the side, they also install the PVD at below the embankment here to drain out the water from the vertical PVD. So this is the general configurations. This is the input parameter. I'm not going to go deep into it, but general principle is that all the parameters are correlated to 1D consolidation parameters for soft clays, lambda and kappa, and also correlated to SPTN for the residual soils. And we use the soft soil creep model to simulate the behavior of the soft clay and hardening soil model for the residual soils. Now a bit of descriptions on the model that we use in this example. We use the Midas GTS NX version 2022 in this analysis. We have been using this software since 2010. We use the soft soil creep model because we want to model the creep in the soft clay. Now most of the programs nowadays were coded to only calculate the creep after the end of primary consolidations. However, the soft soil creep model in Midas GTS consider the creep once you load the soil and then couple with the primary consolidations. So this is very important. Most of the software cannot do this. The soft soil creep model is similar to the modified chem clay model, but it has 2 caps for the yield surface. On the dry side, it follows the modified molecular model, and on the wet side, it follows the elliptical caps in the chem clay model. Soft soil creep model can compute the creep, but modified chem clay cannot. Some features on the soft soil creep model. The stress path in soft soil creep model is stiffness dependent. It is able to model the loading and unloading in a single set of parameters. Unlike molecular model, you have to use 2 sets of parameters to simulate the unloading and the reloading. And it has memory of pre-consolidation pressure. And it has 2 caps for the yield surface, as I explained before. And soft soil creep model is not complex. It's not that complex, but it's enough to capture the behavior of the clay. There are 6 input parameters in the soft soil creep model, and it's very simple. You can get the parameters from 1D console and or triaxial test. A little bit information on the constitutive model. A figure on the top illustrates the yield surface in the PQ plane, in the PQ plane. And the bottom figure illustrates the same yield surface in pi plane. The yield surface cap can expand when the PC is reached, it's very similar to the modified Chemclay model. Now, the total strain in soft soil creep model is a summation of elastic strain and plastic strain, and so the creep part, the creep strain. The plastic strain rate is a function of derivative of plastic potential. And the creep strain is a function of consolidation parameter like lambda, kappa, and the E naught. And tau is a day one. P equivalent is given by these equations, and PP is the pre-consolidation pressure. Now, these are the formula for the yield surface. F1 is the function for the surface at the dry side, and F2 is the function for at the wetting side. And the plastic potential follow the rho stress dilatancy theory. It's not the associate flow rule model. Now, this is the gist of this modeling. How do we model PVD in the Midas GTS NX? We refer to Indra Ratna's work. His paper is quoted below. Now, what it does is that we convert the axis symmetry radial flow in the PVD into a plane strain condition. Once we know the dimension of the PVD and the mandrel, and then we can calculate the BS, is the width of the smear zone in plane strain. Now, if you know the KH, or the permeability in horizontal directions from the lab test, we then can calculate the horizontal permeability in plane strain condition. Then we can downgrade it again to consider the smear effect, and then we have got the K prime HP. You can get all the information from this paper. And once you know the BS, the dimensions, and also the permeability in plane strain model, you then can do your geometry modeling in Midas GTS NX for every rows of your PVD, and you apply the plane strain permeability here for every rows of PVD, and then you can apply you can apply a zero head boundary along the PVD to simulate the drain condition along the PVD. Now we simulate the constructions of the embankment closely from the site record in Midas GTS NX. Basically, we generate the initial ground stress, and we install the PVD, and we start filling the embankment 300 mm per lift, 4 days per lift, and lastly we consolidate the ground for 20 years. And you can see that the analysis is time dependent, so you need to know the input time. Now we look at the results. These are the settlement measured below the tri-embankment, plotted in a log scale in time in x-axis. This is the settlement. This is the days of the consolidation plotted in log scale. The maximum settlement after about 400 days, when we got the result, is around 1.3 to 1.6 meters. The piezometer results, piezometric results, which I will show you later, shows that indicated that at this point of time, the dissipations of the excess portal pressure is almost completed. So from this point onwards, the secondary consolidation settlement will take over the primary consolidation settlement. You can see it start to turn. This is our initial predictions without creep, which is not very good, and these are our predictions. I will show you the result later. It predicts a better settlement curve compared to if you don't consider the creep. Now, if you look at the creep, it gives you an impression of increasing with time. It can go infinite, but if you extract the numbers into a natural scale, you can see that it's not the case where over time the creep is actually slowed down in very much manner. For example, the creep reduces from 100 mm at the first year compared to the 1.6 mm only per year after 15 years. Now, this is the rate of settlement plotted against time. The rate decreased over time, but not reduced to zero. So because they are creeps, so the rate of settlement is still reducing, but not going to be zero. Now, this is another measured settlement at the lower embankment, or we call it at the stabilizing berm. There's no PBD installed in this area. PBD only installed at this area, not here. So you can see the settlement is very much smaller. The total settlement will be the same, but the rate of settlement is very slow because there's no PBD installed at this area. And this is our simulations. Means to say that the settlement the record is still early compared to the ultimate settlement. Now we look at the pore water pressure versus time. The excess pore water pressure is generated when the loading is applied onto the soft clay during the constructions of the embankment. The excess pore water pressure is also dissipated during the constructions process, during the build-up of the field on the embankment, because this is a fully coupled effective stress seepage analysis. The line with the denser curve is the measured excess pore water pressure. So it jumps up to the maximum when you load the embankment, and you reduce with time during the dissipations. And these line with lesser markers are our predictions. It's actually very good. Okay, you can get the response and also get the magnitude right. Now, if you look at the excess pore water pressure versus the applied load, see what is the response of the excess pore water pressure versus applied pressure. This group of lines is the measured excess pore water pressure. These group of lines are our predictions. Not very good in parameter matching, but the response can be captured. That's all we can say. Now, we also compare the inclinometer installed somewhere at the toe of the main embankment. So if you look at the deflections here, the inclinometer deflected 200 mm, and this is our predictions. It's not too bad. And the orange color lines is the long-term conditions. So say after 20 years, you will get 350 mm. So our predictions will be comparing this line to this line. Is very good. Now this is a settlement profile across the embankment, below the embankment. So the embankment is here. So this is a settlement profile below the embankment. This is the measured settlement profile below the embankment. This is our predictions for 10.5 meter thick soft clay. And the black color lines are the long-term settlement. So we can capture not only the shape of the settlement, and we also can capture the settlement, the magnitude very correctly. Now this is the excess pore water pressure in the ground when the embankment is filled to maximum height, that is plus 4.65 meters. Now using this type of modeling techniques, the excess pore water pressure in the PVD is zero because we apply a zero head along the PVD, and the excess pore water pressure in the soft clay in between the PVD dissipates over time. Now you only can get this type of analysis results when you do when you model the PVD for the individual's PVD. You cannot get this type of output when you use the equivalent, using the equivalent permeability for the clay treated with PVD, like that one introduced by the Bergado. So it gives you a better results and better output using this method. Now, after 20 years, the excess water pressure is fully dissipated below the embankment, but not at the stabilizing berm because there is no PVD here. Now, this is the total deformations of the embankment when it's built up to maximum height. The maximum settlement is about 660 mm. And this is the deformed mesh for the long-term settlement. It records 1.7 meter settlement. Now, these are the conclusions we can draw for our analysis for tri-embankments. We have two more embankments, zone 4 and transition zone, will come later. Number one is that we say that the soft soil creep model that allowed for primary and secondary consolidation occur at the same time in Midas GTS NX give a reasonable good match with measurement. Second, we say good match with measured excess water pressure, settlement, and the lateral deformation. And third, we say that you can use the Midas GTS NX to estimate the post-construction settlement, including the creep. Now, for this example, the post-construction settlement for the tri-embankment is about 200 mm for the next 20 years. Now, I have presented earlier the result for the tri-embankments. Now we look at the transition zone and the zone 4. I will show you the ground here is more permeable and less compressible, and therefore we have optimized our design or rerun our design analysis to capture the deformation behavior. Now we compare the soil characterizations from CPTU results for the tri-embankments here, in the transition zone and the zone 4. You can see that from the CPT test, you are able to recognize the soft clay is 12 meter thick. The clay in the transition zone is intermittent and is thinner, and there's no soft clay in zone 4. When you use a CPTU test result, you have to be very careful. You have to calibrate your CPTU results. Too many informations from the CPTU. You just have to be careful on what you use. Now we compare the cone resistance QC, constraint modulus, EOED, lambda, U2 is the pore pressure at the cone, at the tip of the cone, and KSBT is the permeability from the CPTU. We compare all those parameters between three embankments, the tri-embankment, transition zone, and the zone 4. From the results, you can see that it's very consistent to tell you that for transition zone and zone 4, the QC is much higher than the tri-embankments. The constraint modulus is higher compared to the tri-embankments, and therefore the lambda is lower. Is stiffer in the transition zone and the zone 4. And for U2 versus depth, you can see that for transition zone and zone 4, there are many sand lenses in the soft clay, and therefore it's more permeable compared to the tri-embankment. You can see the orange color line is quite homogeneous. There's no sand lenses in the soft clay, and KSBT from the CPTU test, you can see that for transition zone and zone 4 is more permeable compared to the compared to the tri-embankments. So all these parameters indicates that the clay at the transition zone and zone 4 are less compressible, more permeable, and we have thinner clay layer. Okay. From there, we then can improve our model for the transition zone and zone 4 with the less compressible and more permeable clay by referring to the CPT result that I explained to you earlier. This is a finite element mesh, 2D only. We don't need to do 3D for the transition zone. The embankment height is 3.1 meter, thinner soft clay layer compared to the tri-embankment. Tri-embankment, we have 10 meters. Now we have 6.5 meters only. So therefore, you expect lesser settlement and faster rate of settlement. Now, the basic principle on how we derive the parameters for tri-embankments remain unchanged. We only change the only change that we made for the transition zone is to use a higher permeability and the lower lambda value for the clay by referring to the CPTU results. We adopted two sets of parameters for the lambda value simply because the CPTU result tells the lower lambda value, and from the 1D console test we have a higher lambda value. And these two sets of parameters give a very reasonable result, forming an upper bound and lower bound settlement prediction curve. Again, we follow closely the constructions of the embankment at site closely. And now we look at the measured settlement. The maximum settlement at 290 days is about 0.1 to 0.15 meters, which is much smaller than the tri-embankments, as evidenced by the CPTU results also. The pore pressure at this stage is almost fully dissipated, I'll show you later. And the secondary consolidations starts to override the primary consolidation. You can see there's a small turning at this point of a settlement curve. The gray color line is our predictions using the lower lambda value, and the orange color line is our predictions using the higher lambda value. And the measured settlement fall within the upper bound and the lower bound. Now, since the soft soil is more permeable, the generated excess pore pressure is very small, about 4 kPa only. But we still manage to capture the response and also the magnitude. Now we do the same for zone 4, another embankment. This is the mesh for the zone 4. The maximum height is 3.7 meters. Below the embankments are the PVD throughout, including the stabilizing berm. Now, similar to transition zone, we adopted a more permeable and less compressible parameters for the clay by referring to the CPTU results. Again, there are two sets of lambda parameters used simply because the 1D consolidation result give a higher lambda, and the lambda from the CPTU is lower. Again, we follow closely the construction stage happen at site, about 300 mm per leaf in 7 days. So this is the result. Settlement plot against time in log scale. We are able to predict the settlement fairly well. Okay, there are a lot of noise here because I think this area is more permeable and more sand lenses in that area. Again, our model is able to capture the response of the pore pressure buildup. Okay, this is our predictions. This is the measurement at the right magnitude. And for zone 4, our simulations compares well also with the measured deflections in inclinometer a few meters away from the embankment. These are our predictions. This is the measurement. Now I would like to draw the following conclusions for the transition zone and zone 4. Number one, we say that the soil properties at transition zone and zone 4 are different from that at the tri-embankment. The soil in the transition zone and zone 4 are less plastic, less compressible, and thinner. And number 3, we say that the measured settlement is significantly lesser compared to the tri-embankments. And CPTU results provide data for quantitative assessment with coupled finite element analysis using Midas GTS NX. And the computed settlement closely similar to the measured settlement. And that's all we say for case history number 1. Is it too heavy? Let's continue before we go to the tea time. Now we look at second case study. It's about an excessive movement of a jetty in which the berthing platform was moving away from the jetty and form a crack on the walkway. Our objective for this exercise were to establish the possible mechanism of the excessive movement and to carry out the quantitative assessment of the jetty. And we also need to evaluate the forces in the existing pile and other jetty structures because the clients want to know whether the piles and the jetty are also are in the good conditions after the movement. If not, then we have to propose a long-term solutions for the jetty. Now this photograph shows the cracks at the walkway. This is the crack from this is a tie beam, and this is a walkway, and this is a construction joint. So this side is going to the river, and this is the jetty. So since the slope move, and then the berthing platform also moved to that directions, and we recorded the contractor recorded the cracks and the gap. This is a layout plan of the jetty. I give you a better illustration. This is the river, river, and then this is the jetty. This is the berthing platform. This is a loading platform. Dolphins are here, and cracks happen here. So what we were guessing at that time before the analysis is that the slope here along the river has accumulated a thick layer of silt, and therefore, over a long time, silt has accumulated on the slopes. Then it forms a lateral force applied onto the steel pipe piles that's supporting the jetty. So over time, the cracks propagate, and they ask us to analyze. Now we look at a new survey along the slopes of the slope along the river and superimpose onto the original slopes. Then we know the height of the silt accretions for every section, section 1 to 4. The height of the silt accretions is about 12 to 16 meters. It's very high, and 16 meters is about 3-4 stories of condominiums. Below the silts are soft clay. These are soft clay. It's very common, soft clay. Once we got the cross sections, then we can import them into Midas GTS NX to create a 3D model for the slopes. This is the consistency of the silt material. The moisture content is about 60%, and the plastic limit is about 40%, and the liquid limit is about 80%. What it says is that the silt material is not strong. It's not strong. It's not strong. It's weak. The plasticity of the silt is about 30%. The measurement of the crack indicated that the opening is widened over time. They measure the gap over time. The maximum gap they measure is 275 mm. So we got some numbers to match in Midas GTS NX. We back calculated the friction angle of the sealed material using a very simple slope stability analysis. And we assume that the slope is at its repose angle. The back calculated value was about 24 degrees for friction angle for the sealed material. Now this is a three-dimensional mesh of the jetty. We only model half of the jetty, taking advantage of the symmetrical geometry of the jetty. The subsoil was represented by 3 layers of soils, soft clay on top of 2 layers of residual soils. The thickness of the subsoil follow the thickness in every borehole positioned especially in this model. The jetty, berthing platform, and the loading platform were modeled by using 2D shell element. Okay, and the jetty was supported by a lot of steel pipe piles, about 100 of them. The steel pipe piles were driven into the ground and were infilled with concrete at the upper part of the pile. You can see the different colors. So we can model all this in Midas GTS NX. This is infill concrete, this is without infill. To increase, the purpose of infill the steel pipe pile was to increase the rigidity. And there are 3 construction joints in which were connected by the tie beam. So there are 3 construction joints here, 1, 2, and 3 construction joint. The construction joint is, the slab is not connected, but it's only connected at the 2 sides by the tie beam. I'll go in great detail later. This is a layout plan of the jetty, looking from the top, and this is the elevation view of the jetty. Now this is the details of the tie beam. There are 6 number of T16 rebar in each tie beam. We model the construction joint by deactivating the 2-dimensional shell element, and the tie beam by activating the 1D element for the tie beam. The slabs have different thickness. We can consider all this in Midas GTS NX. There are 2 different pile size for this jetty, and different depth of the concrete infill were modeled into the Midas GTS NX. So we do a lot of works to model the steel pipe pile correctly. There are 2 sizes. One is the 711 mm OD, and the orange color is the 914 mm OD steel pipe pile driven into the ground. We computed the shaft resistance and the brace resistance by referring to the Imperial College pile method. And we construct the load settlement curve by referring to our recent works. Published in the CRC press, going to be published next year. Next year. So we need to construct this DZ and QW curve so that we can input into the Midas GTS NX. We also model the tidal fluctuations by changing the water head on the slopes. So this is a high head and this is a lower head. So we want to simulate the tidal force on the slopes. However, the result suggested that the influence of the silt accretions to the movement of the jetty is much profound compared to the tidal fluctuations. So what it means is that the silt accretions accumulation is much profound compared to the tidal effect. For this case study, we carry out 3 analyses. In case 1, we first simulate the elastic tie beam in place and accretion taking place until the ultimate tensile capacity is reached. From this analysis, we know the critical height of the silt when the tie beam start to fail. In case 2, we then apply the mooring load on the jetty at the critical height to simulate the opening of the gap. In case 3, all the external loading were removed and the silt were completely removed and the tie beam were repaired. Then the mooring load is reapplied to simulate the working conditions of the jetty in long term. Now in the next few slides, I'm going to show you the construction stage in 3D model. So for stage 1, we generate the initial ground stress. This is the mesh. The initial water table is at the mean sea level, 0 meter. Then we construct the jetty. We then apply the load on the jetty to simulate the operational condition. Now I have shown earlier that the tidal fluctuations had little effect on the permanent deformations. Therefore, we simulated the highest and lowest tidal tides, highest and lowest tide in the 3D model. For these steps, the silt starts to accumulate from -16. Sorry. Yeah, starts to accumulate from -16 to -14.8, and the silt continue to accumulate until the maximum height. Then after that, all the external loads were removed and silt were excavated. Then we reapply the service load of the mooring force to simulate the operational conditions of the jetty. So these are the construction stage. From the first analysis, this is the result. We know that from this analysis, we know that the tensile capacity is reached when the silt reached the height of -5.2, is at the mid height of the slopes. Then in second analysis, we are able to match the opening of the cracks of about 275 mm. This is the measurement. So from minus GTS NX, you can simulate the whole history of the opening of the gap. Then this is the removal. This is the gap when all the silts are removed. So we can simulate the complete history. This is a total displacement of the jetty at the maximum accretions of the silt. The maximum movement occur at the locations where the crack observed. So the deformation pattern and the shape is very reasonable, judging from the observations from the site. And the jetty moved backwards. Backwards means move to that directions when the silt is completely removed in the third analysis. And this is the total displacement of the slopes when accretions of the silts reach the greatest height. The maximum movement coincide with the locations of the cracks. We didn't manipulate anything. We just key in the parameters, the geometry, and this is the result. It tells us very, very real of what happened at the site. Now this is the movement of the slab. We are able to simulate the separations here. Separations at the construction joint. And we're also able to simulate the magnitude, 275 mm. Now we look at the axial forces in the steel pipe piles. Compare against the structural loads, structural capacity. This is structural ultimate capacity, and this is the geotechnical ultimate capacity. This is the pile number, and this is the axial force. So when the silt accretions reaches greatest height, so you expect some of the pile may fail. Okay, so the axial forces in the steel pipe pile exceed the geotechnical capacity. This pile exceeded, and when the silt is completely removed, then the axial load in the pile reduced to below the SLS, the working load conditions. The tensile force in the pile is not a problem, it's small, negligible. So you may ask what happens if the pile fail in the model. So it will distribute to the next pile. So that explains why the model is still able to converge. So the following conclusions we can draw for this analysis. Number one is a comprehensive analysis of the effect of the silt accretions on jetty was carried out using Midas GTS NX. Next, we say that the analysis shows the maximum force in tie beam at the locations of the observed cracks. The tensile capacity exceeded when the critical height is minus 5.2 meters, which is about at the middle of the height of the slopes. Next, we say that the 3D FE analysis was able to match the gap opening. And number four, we say that the siltations increases the axial load in the piles due to down drag. And we also say that complete removal of the silt is desirable. And we also say that the regular dredging to keep the siltation at safe level is very much desirable. Now I'm going to show you the third example. It is about the floating pile design in soft clay. The objectives are to, number one, to carry out a Class C predictions of the excessive settlement of the slab. And then we design a floating piles for our clients to take the high load of steel coil for a factory. And number three, we predict the long-term settlement for the slabs. Now, this is a warehouse used to store the steel coil. It looks very small, but you know the density of the steel is 79, about 3 times higher than the soil. So it's very, very dense material. And the slabs suffer excessive settlement over time and has affected their operation. So our clients come to us, ask us to design a new slab for them. The point is that the slab has settled sagging like this, okay? Now the slab settle at the middle and it drags the column horizontally, and the cracks were observed at the interface between the columns and the slabs. And tie beam was disconnected by the clients. They do themselves, cut by the clients to reduce the effect on the column supporting the portal frame. Now this is a settlement contour of the slab after 10 years of consolidations. The maximum settlement is 450 mm, measured at the center of the slabs. This settlement contour were taken by precise leveling recently. Now, deep boreholes indicated that the soft clay is around 25 meters. There are some veins on top, so it's a soft clay layer. Below the soft clay layer is a residual source before reaching the bedrock at about 45 meters. It's not so important. Important is the soft clay. The consistency of the clay suggested that there are 2 distinct layers of the clay with different strength, being the upper layer is softer than the lower layer. There are 2 distinct layers. The E0 is about 2.5 and the compression ratio is about 0.35, and the OCR is roughly about 1 except for top part where the clay desiccated. Now the undrained shear strength is about 25 kPa to 30 kPa. The undrained shear strength is higher compared to the strength of the normally consolidated clay due to gain in strength over time due to the loading applied on the slabs. Now I want to explain a bit on how we check our model when we model the soft clay in Midas GTS NX. Normally we have data from the vein shear test, undrained shear strength. So, but when you model your clay with chem clay model or modified chem clay model, you are not inputting the undrained shear strength, but you input your effective stress parameters. So what we normally do is that we check the profile of the undrained shear strength in our numerical model by using the Chi equations. You key in the effective stress parameters, you know the vertical stress, you know the horizontal stress, and then you can draw the undrained shear strength from your numerical model using the chem clay model. So I illustrated here is a very typical vein profile, the undrained shear strength profile from the vein. I took it from the Moa clay. This is the black color lines. You actually can model the undrained shear strength very correctly, almost perfect, using the modified chem clay model with this set of input parameters. This is very common for Malaysia, for the clay in Malaysia. And the upper part you can simply model by simple model, molecular model, if you know the cohesion. So all in all, you can actually model your undrained shear strength by checking the undrained shear strength from your numerical model. You have to do this, otherwise you do not know what is your actual undrained shear strength in your numerical model. Now the steel coils were stacked in 2 layers for these factories, and it converted to an average of live load of about 100 kPa. It's very high for about 10. The 100 kPa is about 10-story buildings. So this is our 3D model. We only model a strip of the slabs. The thickness of the strip is 9 meters for illustrations, but it depends on the spacing of the pile element we use in our analysis. And the width of the model is 79 meters, enough to get rid of the boundary effect to the portal frame. This is the portal frame, okay? And we modeled the existing piles and the pile cap that supported the portal frame. And we also modeled a tie beam. This is a tie beam. And we apply a roller boundary along the long directions, and the model is restrained from moving in X directions in these boundaries, short boundaries. And the water table is 2 meters below ground here. Now over the years, we found that using the Imperial College pile methods, it works very well for the displacement pile, including precast RC piles or jack-in piles or steel pipe piles. The method considered the installation effect in the calculations of resistance, base and the shaft resistance using the effective stress method. Now I extract, this is the extract from the ICP manual. It clearly stated that the total stress method is fundamentally flawed, in which many people are still using this method to calculate the bearing capacity for the pile in soft clay. So what it says is that you should use effective stress method rather than the total stress method in the ICP pile method. Now we always verify our analysis with measurement. There are 2 MLT tests here. One is the 1005 mm outer diameter steel pipe pile, 85 meter long, and driven to about 78 meters. This is the MLT test result without concrete infill. This is the MLT test result with concrete infill to about 50 meters, top 50 meters. What I want to show you is that the ICP pile generally gives us very, very good result of the load settlement curve compared to the measurement. And this is our simulations using Midas GTS NX 3D model compared to the measurement because the ICP pile method cannot model a concrete infill condition. So we have to use a Midas GTS NX to simulate a 3D concrete infill model. Now, go back to our slab problem. This is the construction stage. Stage 1, we generate the initial ground stress, and then the groundwater table is at 2 meters below ground. Then we construct the pile supporting the portal frame. Then we apply the live load from the coil, and then we consolidate the ground for 10 years. Then the result from this stage will simulate the conditions we went in to investigate where the slope, where the slab has deflected 450 mm. Then we remove the tie beam, and then we disconnect the slab here, the thin slab, from the pie cap supporting the portal frame. Follow what exactly happened at site. Then we simulate our rectification work by adding the piles in the ground to reduce the settlement of the slabs. Then we apply the live load to simulate the operational condition. Then we consolidate the ground for 30 years. Now we have carried out 13 cases of analysis. I'll just briefly explain to you. Case 1 is the back analysis without piles that simulate the conditions before we went in that give us a large settlement on the slabs. The remaining cases are using different types of piles, RC piles, 300 micropiles, board piles, cement mixings with different pile lengths. These are the floating piles, okay, 18 meters, 12 meters, floating piles, and different spacing and different slab thickness to give our clients an optimum design. Now, before we model piles in Midas GTS NX, we need to estimate the bearing capacity of the single pile, and we develop the load transfer curve. Then we can import into the Midas GTS NX. So I just simply explain to you, for instance, for RC piles 200 by 200, this is the load settlement curve we predicted from ICP pile method for 32 meter long piles, and you will get a lower bearing capacity as the pile getting shorter. So we can get all this response and we can input into the program. Now we look at the results. The blue color lines is the measured settlement profile across the slabs, and the orange color line is our predictions. We are able to match the shape and the magnitude of the settlement in Midas GTS NX. This is Class C predictions. So we are not saying we are very good, but Class C predictions, we must be able to match the number very correctly. Now we look at the results of the analysis. This is the maximum settlement of the slab plotted against time for using the RC pile in the repair works, and this is micro piles, board piles, and cement mixing. So this is a settlement curve. You look at the blue color lines. Okay, this is a settlement curve if there's no interventions for the slabs. So you will continue to settle to about 1 meter in the next 40 years. So we can simulate the complete history of the slab settlement. Say at this point of time, the slab will all the load on the slab will remove, then the slab will rebound. Then this is the settlement curve for using the RC pile, 32 meters, and you will give a distortion angle of 1 in 500. And if you use the shorter piles, 80 meters pile, you will get 1 in 100, and this kind of numbers. All in all, we say that if you use RC pile 200 by 200, you will get a very minimum settlement in the future. And this is also acceptable by our clients because it's very sensitive to their machine. And when we use micropile, floating piles, board piles, and cement mixings, the distortion angle are all greater than this number. So floating piles, very short floating piles are not suitable for these projects. Now we look at the excess water pressure generated in the ground. If there is no piles, the maximum excess water pressure, the maximum value is very near to the slabs. Follow the stress bulb in the stress bulb theory. The maximum excess water pressure generated at a greater depth at the pile toe, if the piles were used. This is 80-meter piles, and similar phenomenon happen when when you use a 32 meters long pile. The excess water pressure generated at the toe of the piles. Now this is the axial load profile in the RC piles. The maximum load is not at the top of the pile, but is at certain distance below the pile top due to the drag load. So in design, we need to make sure that the maximum load in the pile due to the negative skin frictions kicks in is always less than the allowable structural loads of the capacity of the pile. Now we look at now from the 3D analysis, we also notice that the bending moment in the existing pile that's supporting the portal frame also exceeded due to excessive settlement of the slabs. And now I would like to conclude this analysis by these following conclusions. Number one is that the back analysis shows good agreement with the measured slab settlement. This confirmed the slab was not piled, and the back analyzed parameters were deployed in the subsequent analysis. The slab pile with 32 meter long RC pile, 200 by 200, spaced at 2.25 meter centers, provide the manageable level of long-term settlement at 26 mm compared to the 573 mm if you don't pile the slabs. Full history of consolidations and stress change in the ground has been modeled. This is very important. Now I have another maybe 6 slides before I end my presentation. This is the last example. This is the example to show you how we model the negative skin frictions in the Midas GTS NX. Our client wants to build a temporary platform to enable them to launch a jacket into the sea. The design life of the platform is only 1 year, very short period of time. So the question they posed to us was, what is the negative skin frictions after 1 year? Now, if you use hand calculations to calculate the negative skin frictions, then it will give you a very high value, and your design of the pile will be very heavy. Now, this is the ground conditions, 36 meter thick soft clay over a dense sand, and we design a 42 meters long 500 mm diameter span pile. Just terminate the pile in the first layer of dense sand. We don't want to go beyond this layer because there's no point to go beyond because the bearing capacity will not increase. And we were told also that the ground was settling at 36 mm per year. This number is very common in Klang Valley, Klang area for the untreated clay. So what we did was we apply an arbitrary pressure onto the ground. Say in this case, we applied 30 kPa on the ground. Then we adjusted the permeability until we get the settlement of 36 mm per year on the ground surface, like this. Okay, we match this number of settlement in our 3D model. And this is a long-term settlement, not very important. Now we look at the results. The axial load increased with time. Okay, this is the plot of the axial load in the pile increased with time. This is 1 year, 3 years, 1 year, 2 years, 3 years, and so on until 30 years. So what we say is that the drag load developed in the pile is very small after 1 year. So when you use a hand calculation, you tell your clients to use this curve in the pile design. So you give a very heavy design for your piles. From this graph also you can see that the neutral point is about 0.75 times the soft clay thickness. It's like what you see in your textbook. Next, we look at the excess port pressure profile in the clay around the piles. So the excess port pressure is generated when you load the soft clay and then you dissipate in these directions. It's very similar to your 1D consolidation's excess port pressure profile. And this is a ground settlement versus depth for different time. Now this is another verifications of our predictions using the Imperial College pile method. We just got this result a few days ago. The blue color lines is our Class A predictions. Class A predictions means we predict before the test. And the orange color lines is the measured long-term, is a measured load settlement curve from the MLT test. And what I can say is that it's a perfect match. You cannot get any better than this. Now, concluding remarks, I would like to draw the following conclusions for today's presentations. Now, Midas GTS NX is a very powerful tool and it solves most of the problem in our design. It has been demonstrated that the software is capable in simulating the complex geometry, modeling the behavior of the soft clay, and it has been successfully applied in the 4 examples that I show you today. Yeah, thank you for your time.